Hi scholars, today we're going to talk about exponential growth, and in particular we're going to talk about simple compound interest. One example of compound interest is when you put money in the bank, right? So for example, if I put, let's say, $500 in a bank, and that bank tells me that they're going to pay me 2% of interest, of annual interest. Another way they could say that is they're going to give me 2% annual rate of return. What they're saying is that basically after 1 year, that's what the word annual means, I will have from my $500, I'm going to have my $500, of course. They're not going to take away that money, and they're also going to give me 2% of that $500, right? Which in this case is they're going to give me another $10, right? That's not too bad. Okay, so I made $10, which means at the end of 1 year, right? So at the end of 1 year, I would have 500 plus this 2% of my 500, so plus $10. So altogether, right, I would have $510. Okay, and now where the compounding happens is now I have, if I want to look about what happens in my second year, I have $510, right? I have more principal, and if they're going to pay me again 2%, they're going to pay me that 2% of my new principal, right? My new amount of money. And so that's where compounding, that's how compounding can really help your money grow, right? Because after every year, you have a new principal, a new amount of money that you could invest, right? And if the question is, we saw, right, that 2% of 500 was $10, right? And 2% of $510, well, it's going to be a little more than $10 because you have an extra $10 in which to get that 2% of interest, okay? So let's take a look at what that looks like in a formula. So in a formula, the general exponential model that we use to calculate compound interest looks like this. It's a function, right? It's a function that's a function of time, right? Because of course it matters how long you keep your money in a bank, for example. And it's basically dependent upon 3 factors, right? So one is the initial amount that you have, right? That's $500 in our last example. The second thing is the growth factor. That was that 2%, right? And we say that the growth factor B, we define it as 1 plus or minus R, where R is the percent increase or decrease per unit of time, every year, for example, in decimal form. And so if we wanted to rewrite this equation, right, or this function, right, so we had f of t equals a times b to the t power, right? So if this is our b, we can actually just replace 1 plus or minus r, and all of that raised to the t power. And you might ask, well, when is it plus and when is it minus? Well, if I'm growing my money, or if something is growing, then I would use plus, right? And if something is shrinking, I would use minus, of course. So that could be, for example, decay, right? So maybe every year you lose a certain amount of value. And what makes it an exponential model, the reason why we're talking about exponential models is that you are compounding every year a certain number of times, right? We saw in the previous example, that I was essentially going to be multiplying by 0.02 one time, and then I would do it again to the new principal, and then I would do it again, and then I would do it again. And repeated multiplication is in fact exponentiation, right? And so that's the reason why this is an exponential model, okay? So let's take a look at a couple examples of this. Immediately after Basaru buys a car, it begins to depreciate in value. So depreciate means it gets less, right? It begins to decrease in value, and this makes sense. When you buy a new car, it costs more than a used car because the used car lost value. So the value of the car, V, in thousands of dollars, k years after you buy it is given by this following function. So V of k, so this is a function. This is function notation. Okay, so this is the function that says you tell me how many years, you tell me what the input is, how many years it is since you bought the car, and I'm going to tell you what, right, the value of the car is in thousands of dollars. And here's our equation, 22 times 0.87 to the k power. Okay, so immediately this makes sense because we talked about how the number of years is sort of representing the number of times that this thing is either increasing in value or decreasing in value. So it makes sense that the k is in the exponent place. So what do the numbers 22 and 0.87 represent in this situation? Okay, well, the number 22, this is our initial amount. This is our starting amount. Right? If we go back to our formula, we'll see that that's the a value there. So the number 22 in this case means that the car, when you bought it, was worth $22. No, of course not, right? It's the value of the car in thousands of dollars. So this means the starting value was $22,000, okay? This is how much your car cost. Okay, so car costs this much. And the 0.87, well, is that number is less than 1, which means that every time you every year that passes, your value is getting less, because when you multiply 22 by a number less than 1, it gets smaller and smaller. And so we want to ask ourselves, well, what percentage decrease does 0.87 represent? Right? And remember from the last couple of weeks, 0.87, that's really the same thing as like 1 minus 0.13, right? These mean the same thing. They're the same number. And that 1 is our home place. This is 100%. If the car did not decrease in value at all, it would be 22 times 1, right? $22,000 times 1. So instead, it decreases by 13%. Annual rate of decrease, right? So that's what these two numbers mean, what they represent. Now the question is, what will the value of the car be in 5 years? Now that's easy, that's great. That's asking you to calculate, right, this function value. So instead of saying that v of k is this value, let's calculate v of 5, right? When I input the value of k equals to 5, right, what is my output? So v of 5, well, that's going to be 22,000 times 0.87 to the 5th power, right? Every year you do it once, twice, 3 times, 4 times, 5 times, and we can calculate that. So I can type in 0.87 to the power of 5. Plug that in your calculator, and yeah, that makes sense. It gets smaller and smaller. And I can multiply that by 22,000, right? And I'm just going to multiply it by 22 here, and that's going to tell me how many thousands of dollars this thing is worth now. So the answer is that after 5 years, it was worth $10,965. There we go. So $10,965. Okay, let's take a look at one more example. Write an equation to represent the following situation. You invest $9,000 in the stock market and get a 7.25% annual rate of return. That's pretty good. After 30 years, your stocks are worth K dollars. Okay, so we can just really read off these values and sort of think about our formula, right? So our initial formula was, f of t equals to a times 1. In this case, we're making money, right? We're getting an annual rate of increase. So we're going to do 1 plus r to the t power. So this is our starting place, and we can just sort of match these things 1 to 1. So after 30 years, your stocks are worth K dollars. That's saying that the function output is K. You invest $9,000, so we start with $9,000. And you get a 7.25% annual rate of return. So that'll be 1 plus, and don't say 1 plus 7.25, right? We need to convert 7.25 into a decimal. We do that by taking our decimal point, right? Moving it over once or twice, filling it in. And so this is going to be 1 plus, we can put a 0 in front here. 1 plus 0.0725. That's our rate. And the question is for how long? Well, after 30 years, right? So after 30 years, that's our time. So that's our time. So here we go. This is the value, or this is an equation that will allow you to calculate how much your stocks are worth. And you can just plug those numbers in the calculator and you will get an answer.